Hello everyone. In this video we are going to talk about explicit dynamics simulations in ANSYS. So explicit dynamics is useful when the changes are very fast and the whole simulation happens in a very short time, milliseconds, microseconds, nanoseconds, like impact, collisions, drops, and so on, drop tests. In such situation, the implicit solution used by transient structural analysis workbench is not going to work, as we'll see. And we have to resort to the method of explicit solution that is offered in the explicit dynamics workbench. So the overall differential equation that we have to solve is this equation here, where we have the inertial term, we have the damping term, the stiffness term, and the loading. And here we assume that the acceleration term, the d double dot term, is constant between two time steps. So the d triple dot and the higher time derivatives of d, they're all zero between two time steps. If we use Taylor expansion for the d double dot, and we basically plug in the other, as I said, higher derivatives of zero into the expansion for d double dot, okay, then we can get our update equations for what we call the state space equations in a discretized form as shown here. And discretized means instead of these continuous equations, we have these equations that have time steps in them. So time step number n plus 1, and so on. These are the update equations. And why do I call it state space? Because here I have more than one basically parameter that has to be updated. One of them is d and the other one is d dots, right? So the displacements and the velocities here, they have to be updated. So basically I have these two update equations instead of one that have to be updated. So my dummy variables here are the displacement and the velocity that have to be updated. So these are my update equations, okay? Now, what do we do in transient structural analysis, and what is the implicit solution that is not suitable for impact problems? Let's talk about that. Let's see how we solve these equations, and we use these update equations in the implicit method. So if you look here, if I want to find my displacement and my velocity at the next time point, d and d dot at n plus 1, what kind of information do I need in this equation's dollar? I need the current d, I need the current d dot, which I can have starting from initial condition. I need the time step delta t, which I do have, and then I need the current acceleration and the next acceleration. Well, I do have the current acceleration starting from initial condition. I can most of the time assume it's zero, but the current acceleration, I don't have this information. This term is the term that I don't have, and it appears in both of my equations. I do not have the next acceleration. I don't have it. So how do I get this guy? Right? You see, I have a piece of information missing. Otherwise, this information would work perfectly. So where do I get this d double dot n plus 1? The method of implicit solution says, give it a guess. Guess it. What kind of guess? Well, I start with d double dot n as an initial guess for d double dot n plus 1. So I assume that the acceleration is not going to change, basically. Okay? This assumption is not perfectly correct, okay? Because it can change. It's our assumption, but it does and can change. So here we assume that whatever we have for acceleration at this iteration is going to be the same for next iteration, right? Fine. So let's have some guess for this. If I have some guess, I'm going to plug it into these equations dollar, and I get my next values of what? D and D dots. And with this d double dot guess that I have, I'm going to plug them back into this star equation, right? So I fill for d, d dot, d double dot, mcknf, they're all given, and then see whether the guess I had and these numbers that I calculated, whether they match this equation, whether this equality would hold or not. If this equality holds, what does that mean? It means the guess I had for this next acceleration term was correct, then I'm good, so I accept the new numbers for d and d dot for displacement and velocity, and I go to the next iteration. But if this equality does not hold, it means that this initial guess of d double dot n plus 1 is not correct. So what should I do? I need to update my guess, right? And I should keep updating this guess until what? This equality holds. So what you have is a loop here. If the equation is not satisfied, you have to update your guess for d double dot n plus 1 and keep recalculating, keep plugging into the star equation until the equality holds. Then my guess is correct, then I can go to the next iteration. So you see, here you have a loop within another loop, and this method of calculating d double dot n plus 1 by guesses and updating is what we call implicit solution. Because I don't have a number for it, I'll keep updating it until I get something. And the update algorithm could be something like a Newton-Raphson algorithm. So you have to keep guessing, keep updating the guess until, now the updating the guess is not random. As I said, you can do it with the Newton-Raphson, but you have to keep going until you get to a number, and this takes time because you have loop within loop, right? And what's the problem here with explicit dynamics? Why can't I use it for impact problems? Why can't I use this method for impact problems, or let's say drop tests or something? The problem is this: because everything is happening so fast, okay, if I want this inner loop to converge and the outer loop to converge, I definitely need very small time steps. Otherwise, these assumptions are not going to be true. So I need very, very small time steps, typically nanoseconds. And that makes the overall computation time for this whole algorithm to be very, very large, because your updates are very small, nanoseconds instead of milliseconds. So you have to wait forever until this implicit algorithm gives you any converged solution. So instead, what would you do in explicit is, instead of guessing a value for d double dot n plus 1, you try to basically approximate it, and you try to avoid the inner loop. You try to only have one update loop but no inner loop. Okay, so how do we do that one? The algorithm is this. Initially, let's say I'm given my d and d dots, right? The initial state space variables, position and velocity, are given. What do I do? With those values given, I go ahead and calculate my strains. How do you calculate the strains? Well, D's are the same here as U's, right? U here is nodal displacement, is the same as D. If you want, you can change them and call them D here. That's the same variable, nodal displacement. If I take partial derivatives of nodal displacement components, because nodal displacement U or D is a vector, it has X component, Y component, Z component, right? If I use these equations that we know in solid mechanics or theory of elasticity, then I can calculate my strains, both normal ones and the shear ones, right? By taking partial derivatives, which we do numerically. Once we have the strains, we can calculate the stresses. We know the Hooke's law to relate the stress to strain. So if I have the strains, I can solve for stresses, both normal stress and shear stress, right? So what else can I do when I have the strains? When you have the strains and when you have the nodal displacements, you can calculate the new volume of each element, right? Because you can find the new dimensions. You can find what? The new volume, and you can find the new mass density, because if you assume that the overall mass is constant, Rho is going to be the mass that it was divided by what? By the new volume. So you can calculate the new mass density. And once you have the new mass density, and this is the mass of the element and the new mass density, and you also have the bodily forces. B here is the bodily forces or the forces per volume, like gravity. Once you have those, as well as the nodal forces, then I can calculate the acceleration term. Now you might say, well, how would you calculate Fn? Well, Fn comes from the stresses. Remember, I said we calculate strain first, then stresses. From stresses, we can always calculate what? We can always calculate the forces. So basically, you go here, from here, you go here, and then from here, you go to what? You go to calculate this Fn, right? Because the forces are the stresses multiplied by the section areas. So you can calculate the forces. And also from strains, as I said, you calculate volumes, and then from volumes, you can calculate what? You can calculate this mass density. So now you can have the dn double dot, the acceleration term. Then you use these update equations for speed and for the displacement, where here, to improve the accuracy, I'm using half steps here. Instead of full step going from n to n plus 1, I go to n plus 1/2. And this is how I update my basically velocity, and that's how I update my what? Position. And if you see here in my update velocity equation, the only term I need is what? The current acceleration, not the next. I do not need d double dot n plus 1. I just need d double dot n, which I have it already here. So now this is my update equation. There is no loop in it. So I can calculate d dot n plus 1, plug it right down here, and that gives me my next nodal displacement. You see here? So there is what? There is no trial and error like this loop. I'm not going to calculate a guess for this and keep plugging into this equation until it's valid. I'm here going exactly in a loop, and there is no loop within loop. So this method is way faster. And since it's faster, I can use smaller time steps, and I can capture the dynamics of a fast moving system like impacts, like drop test and so on. So this is the explicit dynamics. The reason I'm trying to explain all this before I go to the simulation is I want you to have a little bit knowledge of what's going on behind the scene. Now, a couple of other things that you always need for any numerical solution is: one, how much should be the time step? Two, when do I stop the loop? So for the time steps, this is the formula for the time step that you can use in explicit dynamics. It says your time step should be less than f times h over square root of mve. What is this? So in simpler language, instead of this guy, it was actually less than or equal what? H divided by v. What is h? What is v? H here is the smallest element size, and v is the speed of propagation of wave into the material. So three German scientists basically proposed this criterion and said the time step should be smaller than the time the wave needs to propagate through the smallest element. So before the wave can pass through the smallest element, one time step should have been gone, should have been passed. Otherwise, that time step is not basically small enough. Okay, so this is what they suggested. But the question is, what is the velocity of propagation of wave into a rigid object? Well, that is square root of E over rho, where E is the Young modulus and rho is the mass density. Okay, And for rho here, which is mass density, I can plug in as what? I can plug in as mass over volume, right? So this V and that V are different things. This V is the volume, and that is what you can see here. This is this guy. This one is velocity. This is a separate one from this V. So that's where you get this term here, right? This is where you get this guy. H is also there. So you might say, what is this F? This F here is a safety factor, okay? Which typically we consider it less than 1 so that we can even choose a smaller time steps. In ANSYS, by default, this guy is like 0.9. The smaller you choose it, the safer you are in terms of the convergence, but it takes you more time, of course, because you have more and more time steps. Your time steps are going to be smaller. But this is the criterion that is suggested, as I said, by 3 German mathematicians, Courant, Friedrich, and Levy. Okay, and everything here I say is based on the first textbook in the playlists, which is by Professor Hui Huang Li, by his ANSYS book. So everything is coming from his textbook, which is, by the way, an amazing textbook. And this is the time step you should be taking. This is the upper limit of that. And when do you know that you have converged? Here we use energy error. We calculate the current energy of the system and we subtract it from what the energy should be, which is what? Which is basically what we started with and the amount of work that was done on the system. So the sum of these two green entities should be the current energy that you have, approximation of that. This is the current energy that you can exactly calculate. You subtract, ideally the numerator should be 0 because these green entities should approximate the red one, but until you converge, they are not going to be very close. And then we divide it by the maximum of the current energy, the kinetic energy, and the reference energy. So when this energy error is less than some threshold, we say that, hey, now our approximation of the current energy matching the real current energy, so I'm converging. And typically in ANSYS, this number by default is like 0.1. So when it's within 10%, the system will converge, but I'll show you the replace that you can go ahead and change it. So if you want the convergence to be even tighter and you can wait a little bit more, then you can get more accurate results, right? But again, you have to wait a little bit more time. So this is your convergence criteria, the time step, and this is how the explicit method is solving it, as opposed to how the structural transient analysis and implicit method is working. Okay, so this is some background that I want you to know. Now, for this problem, I'm going to show you 2 objects hitting each other. One is a solid cylinder of structural steel, and the other one is a hollow cylinder made of aluminum. And you're going to see when these two are hitting each other with a big velocity, relative velocity, because we're going to fix the solid cylinder of steel and we're going to move the thin shell of aluminum at a speed of 300 meters per second, a large speed, which is close to the sound basically speed. We're going to move it at such a speed and we hit it against the steel cylinder and see what happens to the aluminum one. So the first thing you need to do is to make sure you add that aluminum to the list of your material. So you double click on engineering material and you want to add it. So what you need to do is to find the general, you go to engineering data sources and go to general nonlinear materials. And then here you can add this aluminum alloy nonlinear to the list of your material. Okay, so now if I go back here, right, This is my aluminum alloy nonlinear. The model that we have for it is bilinear isotropic, which, if you remember the previous lecture when I talked about multilinear material, so here you have one slope for the linear region and you have another slope for the plastic region. And here, this is the yield strength for this material. This is the slope of the next region, which is 5e to the 8. Here, for simplicity, I set this slope to 0. So I assume that the material acts basically perfectly what? Perfectly plastic. So without any extra load, you can just have continuous change in the strength. Okay, ideally there is some slope, but here I assume it's 0 just to make this calculations a little bit simpler, right? So that's one of the things you want to add. The other thing you want to add is a failure. And here you go under this failure tab and you double click on plastic strain failure to add this property to your material. And here you type in a number for when, at what strain the material would fail, which means it is going to be basically torn apart, right? The material would break. And here we use 0.75 for the strain at which the material would completely fail under plastic deformations. Okay, so here we provide the properties that we want for the aluminum shell. The structural steel for solid cylinder is going to be the same. So now I right click on the geometry, go to the design modeler, and I create the two cylinders that I have. Okay, so the first thing is I go to the XZ plane, to the horizontal plane. I look perpendicular to it. I go to the sketch. I make sure my units are in mils. And I would draw some circle here at origin. I give it dimensions, 50 mils for diameter. And then I go ahead and extrude it upward. So go to extrude, choose this sketch, apply it, and I use a symmetric extrusion, and in each direction I go up and down for 100 mils, and then I generate it. So I create the solid steel cylinder. And then I'm going to go to the XY plane, and then under the XY plane I create a new sketch. And for this sketch, I'm going to use another circle and draw the circle on the x-axis, give it dimensions. Again, make it the same size, 50, and make sure this guy touches the other cylinder. Okay, so here I use a horizontal offset and provide this offset here and make sure this is exactly 50. So they are touching each other. If you don't do that, you should be waiting a long time before they reach each other. So you always make sure that you start with the two objects touching each other. Okay, and here is your next material that you're going to what? You're going to create. So now for this one, I extrude it again. And again, I make sure it's symmetric in both directions. I make sure the dimension is 100. And then I make sure that here for add material, it is what? It is add frozen. So it is a different material. The other thing is I give it a thin wall. So here I give it 0 thickness, but later I will add 1 mil to the thickness of this. Then I generate it. Okay, so you see here, that's a shell that later I'm gonna make aluminum, make it out of aluminum and apply 1 mil thickness to it when I go to my structural analysis. Okay, so this is my geometry. Now I go ahead and go to mechanical. Here we go, we are in ANSYS mechanical. First we need to take care of the geometry. You see this guy is solid cylinder, but the behavior is flexible. So you change it to solid, rigid, so we don't want any deformation on the steel. And it's a structural steel, it's all good, but the surface body, first of all, you give it some thickness, let's say 0.001 or 1 mil thickness. The other thing is the material, you change it to what? You change it to this aluminum nonlinear alloy. Okay, so now you have what? You have your physical object here set up. Good. Now that I have my material, it is time to go to what? It is time to go to the connections. So here it has some contact region, which we can delete. We don't need this one. We already have something called body interactions. And this body interaction, the difference it has with a contact or surface is it gives you this extra property of, if you look at it, is frictionless. So what is this? Well, in the beginning, when the two objects are in contact, it makes sure that they are bonded. But when this object starts to fail and get apart, it makes sure that as the parts of this object will move against this cylindrical surface, they move without friction. So it allows you to have both a bonded and a frictionless contact at the same time. So this is enough for all of our purposes, and that's all we need really. Okay, the other thing is mesh. Explicit dynamics in general always, let me add it somewhere for you. So you have it somewhere. So let me add it somewhere. Always try to use uniform mesh in explicit dynamics as much as possible. So let's not use always because we say as much as possible. So try to use explicit dynamics as much as you can. It makes the convergence faster. So here I go to mesh, and here I go to this curvature angle, and instead of 72 degrees, I use 10 degrees. So it gives me a lot more mesh elements, okay? And then generate the mesh. If you want, you can use a smaller angle, so it gives you a lot more mesh elements. So this is enough for the sake of this simulation. And now I need to go ahead and set up my conditions. So for my initial conditions, I have nothing, but I need to add an impact velocity. So I right click here, go to insert and add a velocity. And the geometry I want to apply to is this object here. And then the method is components, and it is going to come in this direction, which is x-axis. And I'm going to make it 300 meters per second, a large impact velocity that this guy hits against that object. Okay, and then under analysis solution here, it is asking for an end time. In impacts, probably the duration of impact is very small. You don't need a large computation time because everything happens, as I said, in matters of nano and microseconds. So here I just use half a millisecond. And you see here the maximum number of cycles is basically 10 to the 7. So it can go 10 million cycles of update, right? This is a time step safety factor. Remember this F that I told you, this F, the safety factor, that's what? That is this safety factor here, F. And remember, I told you that the maximum energy error, right, is 0.1. That is this criterion here that I said. So if you want to change F, or if you want to change convergence or time step, this is the place to change it. This is one place, and this is another place. You can change those to change the convergence criteria. Okay, and then once everything is set, I can go ahead and insert, like, let's say, total deformation. I can insert 1 mice as a stress and so on, and then I can solve and look at the results. Before I show you the results, there was one more thing that we need to set up in the simulation, and I forgot to tell you. And here is under the explicit dynamics, under analysis setting, we set up here the final time. There is one other thing you need to add, and that is here. It says on material failure, by default, this guy is off or no. You turn it to on or yes. What does that do? It shows that this material, when it hits against the steel column, it would fall apart and it would fail and it will basically be torn apart. Okay, so if you want to see that, the physical failure, you want to turn this on. So now if I go and look at the deformation, look, here we go, right? If you want, you can change this and make it slower. And you clearly see that, let's look at it in this direction, that how this basically part is going to what? It is going to fail for you. Right? And if you use more time, then it just goes forward. But here, experimentally, the time of half a millisecond was enough to show the failure. And you can see the stress values, which is for this part is 2.8 to the 8 or 280 megapascal, which is way more than the yield strength and even more than the plastic failure point of the material. So clearly the object is failing under the impact velocity of 300 meters per second. Okay, so hopefully this video is useful to you, and hopefully you learned some very basics about the impact analysis and the implicit dynamics. Thank you for your attention. I will see you in my next video.